Hello VMSG, my name's Jamie Farquharson, and today I'm going to be talking about some of the work I've been doing using network analysis to study analog volcanoes. So very briefly, I'll go over the concept of analog volcanoes, then discuss how graph theory can be used to analyze these kind of data, and then just highlight some of the results gleaned from this approach. So as a volcano erupts repeatedly over time, we can establish an eruption chronology. But a key problem that arises if we're trying to predictively model future eruptions is that the size of a future eruption might not be reflected in the prior chronology at all, which is to say that a past small event or a series of past small events tells us nothing about future large events. This can be compounded even further by what a statistician might refer to as a black swan event, and this is when there's a whole lot of nothing followed by a previously unobserved and hence unexpected event. One example is Chai-10 volcano, which erupted in 2008 after a period of around 9,000 years of quiescence. So this is where analog volcanoes can prove really useful. Say we have a volcano, imaginatively named Volcano 1, for which we have only a recent eruptive chronology. If we can find a volcano that is sufficiently similar to Volcano 1, say Volcano 2, then examining the eruptive history of this analog system might tell us something useful about the potential future development of our original system of interest. In this case, we might surmise that the next eruption of Volcano 1 may be somewhat larger than our existing data would indicate. With over 1,400 Holocene active volcanoes, how do we go about selecting analog systems? Some commonly used parameters include the tectonic setting of a volcano, its bulk geochemistry, the size and style of previous eruptions, and its morphology. Each of these, or combinations thereof, have been used previously, but I'm going to focus here on a structured quantitative combination of all 5 of these listed parameters developed by Thiers et al. In their 2019 paper. So the equation shown on screen just establishes an analogy score based on a weighted value of each individual criterion. Using an approach like this, one can compute the analogy score for Volcano 1 against any other volcano, with the highest score representing the system that is most similar, in this case the volcano highlighted by the box. So, some questions. First, are some volcanoes consistently good analogues? By which I mean, are there certain volcanoes that can act as a general archetype for certain tectonic setting, a certain eruptive style, and so on? The flip side of this is, are some volcanoes consistently bad analogues? Are there some weirdo volcanoes out there that can't be compared well with any other systems? And thirdly, can we effectively and hopefully quantifiably group sets of analogues, such that any volcano in the group would serve as a suitable analogue for any other volcano within the same group? Sticking with the work of Thiers et al., but this time an open source incarnation of the same structured analog protocol called PyVolcans, I've been iteratively computing the analog score for each possible volcano pair in the Smithsonian database. The value of AXY, above which a volcano can be considered similar, is also systematically modified. So using these data, a series of network graphs can be built, and I'll describe this in the coming slides. So we start off with a set of volcanoes, computing the analogy score for each possible pair. Each volcano in this instance comprises a node, and the similarity between them comprises an edge, with each graph being described by an adjacency matrix, with the value of the edge being the analogy score computed as discussed earlier. Some of these edges have a high score, shown here in thick lines. Some have a low or a 0 score, shown in dashed lines. And generally, we try to optimize the structure of the graph such that high scoring edges are close together and low scoring edges are far apart. So we're minimizing the distance between very similar nodes and maximizing the distance between dissimilar nodes. We can then quantify how important any given node is, which tells us something about how good the volcano is as a general analog. The simplest measure of importance is the degree centrality, which is just the sum of all of the edges attached to a given node. In reality, it's a weighted sum, but I won't go into that here. We can then form a hierarchy of volcanoes depending on how similar they are to other systems. The next thing we might want to do is detect communities. So I'm going to state without presenting evidence that all of these networks are what we call a small world network, a characteristic of which is the occurrence of cliques or communities within the network, and these communities are internally connected. So I've used a modularity optimizing community detection algorithm to identify communities within the graphs, which seeks to minimize this parameter m on the basis of the number of edges and the degree centrality of the nodes within a subnetwork. So this way we can separate systems that describe all other systems within their subgroup. So now let's look at some real data. This is a network generated using a threshold analogy score of 0.95. As an aside, we can see that these networks are quantifiably non-random by comparison with truly random graphs, which have this kind of hairball structure, rather than the more complex structures we see in the original graph. So this is the distribution of the degree value, which shows us that there are many poorly connected nodes and a few very well-connected nodes. The distribution we might expect from a random graph is shown here in grey. So in this case, there are 9 distinct communities detected. Now, if we were to sort the adjacency matrix according to these groups, we can identify clear structures along the diagonal and very little structure off diagonal, which tells us that the community detection algorithm is doing a really good job of describing the distribution of nodes in the graph. And these trends persist across a wide range of analog thresholds, including these complex non-random graph structures characterized by a particular degree distribution. Community structures are evident and describe much of the variation in the graph distributions. Perhaps more importantly, these communities typically make sense. For example, Kilauea, Badabunga, Piton de la Fournaise, and Cumbre Vieja are all organized into the same community, as we might expect from volcanoes that seemingly share many traits. And this community is separate and distinct from the community that includes Tungurahua, Colima, Marapi, and Mount Rainier, which are partitioned into their own community, steep-sided, explosive stratovolcanoes that frequently produce lahars. So we can also identify clear non-random geographic patterns, which is in agreement with previous work using this tool. So on to some closing remarks. First, complex networks appear to be an effective way of analyzing volcano similarity. It can be used to determine appropriate levels of similarity for different systems. For example, a volcano that has a high degree centrality might require a higher threshold in order to determine the best analog, whereas one might have to be somewhat less stringent for a volcano which has few suitable analogues. This contextualization could prove invaluable in transferring site-specific knowledge between volcanic systems. It can be used to identify volcanoes for targeted future study. If a volcano is not particularly well matched by any other system, it may simply be that we don't know enough about it. Importantly, it allows quantitative determination of communities, such that any volcano within a community can be used as an analog for any other volcano within the same community. And we can also identify volcanoes that are archetypal of certain parameters, such as the eruption style or morphology. And this lends some credence to the idea that we don't necessarily need to study all volcanoes on Earth to an equal degree. It also lets us identify outliers and anomalies, volcanoes that for whatever reason are quantifiably dissimilar to all or most other volcanic systems. So thanks for listening. I'm happy to field any questions, and don't hesitate to get in contact via the details on screen if you want to chat about analogues.